Spurred on by the nation's vast interstate highway program, which began in the mid-50s, lime has become a major soil stabilizer for subgrade and base construction. Before it became popular, highly plastic clay soils like this were generally excavated, wasted, and replaced with better material at considerable cost. Now, with lime, these same soils can be fully utilized thanks to several chemical reactions occurring between the lime and clay. During mixing, a phenomenon called base exchange converts the clay to a low plastic, friable material that the grader can handle readily. Then, after compaction, a pozzolanic or cementing reaction occurs, which greatly strengthens the soil, transforming the treated layer into a firm, all-weather working table. The stabilized layer not only aids in subsequent construction, but also helps maintain the smoothness of the pavement and promotes long-term durability. And all this at low cost, since only small quantities of lime are required, generally 3 to 6% by weight. Actually, the use of lime in road building is far from new. Romans used lime in building the renowned Appian Way, taking advantage of lime's pozzolanic reaction with volcanic soil. This road is still in service after 2,300 years. Moving to a more recent time, in the mid-40s, the Progressive Texas Highway Department began using lime successfully in the recycling of worn-out roads. With this technique, the existing wearing surface and base were scarified. Lime was added, mixed in, and the material compacted to form a new stabilized base. Here's a core taken from one of the recycled roads. Due to the cementing reaction, its strength exceeds 500 psi. The asphalt fragments were part of the original road. Since those early Texas recycling jobs, lime stabilization has spread to nearly every state and most foreign countries. Following the early successes in road building, lime stabilization was soon extended to many off-highway uses, like airfield runways, building foundations, railroad subgrades, canal linings, levees, even racetracks. Another important use for lime involves asphalt hot mixes, where it serves as an anti-stripping agent to reduce moisture damage. Considering this application, along with stabilization, means that lime is now used in all highway layers, from surface course to subgrade, a truly versatile material. The lime used in soil stabilization is not to be confused with limestone, a carbonate rock. For stabilization, you must use either quicklime, an oxide form of lime, or hydrated lime, an ultra-fine hydroxide powder. Lime stabilization does not apply to agricultural limestones, which do not react chemically with soils like quicklime or hydrate. To make lime, you start with limestone. After quarrying, crushing, and screening, the pebble-sized limestone is fed to rotary kilns, where it is heated to about 2,400 degrees Fahrenheit, converting the limestone to quicklime. After cooling, the quicklime pebbles are combined with water and fed to a hydrator, where the second lime product, hydrated lime, is produced. Now let's consider the stabilization construction procedure, first looking at base stabilization on a city street recycling project. Like many under-designed residential streets, this one exhibited typical alligator cracking. The first step was scarifying and breaking up of the thin wearing surface. Additional scarifying to a 6-inch depth revealed the root of the problem. Besides an inadequate base course, the underlying soil was a highly plastic clay, which provided little support. The clay was a bad actor, having a plasticity index, or PI, over 40, with high volume change. Very unstable. After scarifying, lime slurry was spread in 2 passes to provide a 4% application. A rotary mixer then took over to blend the lime, base material, and clay. with several mixing passes needed to pulverize the clay. Even though slurry was used, water was added due to lime's quick drying action. After mixing was completed, a sheep's foot roller was used first, followed by a pneumatic roller for final compaction. The final step was moist curing for several days, after which a new surface course was applied. On another recycling project, a heavily traveled state highway, the asphalt surface course was several inches thick. So, after scarifying, a grid roller was used to break up the asphalt. On this project, traffic was maintained by working one lane at a time. Since dusting would have been a problem, lime slurry was used, being spread between windrows to prevent runoff. Windrow mixing was carried out first, followed by rotary mixing, then compaction. Now, let's switch to the Dallas-Fort Worth Airport to observe subgrade stabilization. Unlike base stabilization, the procedure requires two-stage mixing with curing in between in order to break down the clay clods to a fine pulverized state. Prior to mixing, the soil was first loosened with a root plow to the 18-inch depth of stabilization. Then lime slurry applied in 10,000-gallon slurry wagons. For preliminary mixing, a disc harrow was followed by a train of rotary mixers, each making a deeper cut than the previous one. After pulverization to -2 inches, the soil was compacted lightly and shaped to shed rain, then cured for 2 days. During this period, lime's chemical reaction helped mellow the soil so that final mixing was easy, with only the root plow and single pulvomixer being used for fine pulverization. What a contrast from the original gumbo clay. After compaction, the contractor sealed the stabilized layer with an asphalt emulsion rather than moist cure. An alternate method to in-place stabilization just shown is off-site mixing, generally used for stabilizing thick soil masses. This was the case at a Corps of Engineers slide repair project in Arkansas involving the Mississippi River levee. The clay soil in each slide was first excavated just below the slip plane. The shiny surface, called a slick, bears evidence of the earlier soil movement. After excavation, the soil was picked up and moved to the off-site mixing area. The mixing pads were of equal size, each large enough for a 20-ton truckload of lime. After a pad was built, 5% hydrated lime was spread from pneumatic trucks, mixed in, and the treated soil moved back to the slide excavation. There it was placed in thin lifts, each lift being compacted with crawler tractors. Following backfilling, the stabilized soil was shaped and the slope covered with topsoil and mulch sod. This is one of the restored slides. Lime's versatility in stabilization is evident in the many ways it can be handled. The pneumatic truck is the most common way of delivering and spreading hydrated lime. The lime is blown from each compartment to a spreader bar mounted at the rear. With the auger-type truck, a mechanical spreader is mounted at the rear for accurate distribution. It is driven off the rear axle. Bagged lime is generally used on small jobs, like maintenance, or of necessity in wet areas where the spreader truck would bog down, as on this subgrade job in New York. For slurry preparation, there are two principal systems: batch, shown here, and jet slurry, which is continuous. In this batch setup, 10,000 gallons of water were first pumped into the tank, then 20 tons of hydrate blown in from the truck. Mixing was handled with a recirculating pump, which was also used to load the slurry wagon. It took about 45 minutes to prepare a batch. The slurry was spread in 2 passes, 3% at a time. The truck was fitted with a recirculating pump to keep the slurry agitated during transit. At Dallas-Fort Worth, the jet slurry maker was used. In this setup, the hydrated lime is blown from the tank truck through the rubber hose into the jet slurry mixing bowl, while simultaneously water is pumped to the mixing bowl. There, the hydrate is converted into slurry instantaneously and on a continuous basis, using a water pressure of 60 psi. With this arrangement, a 20-ton load of hydrated lime can be converted to a 30% slurry in 45 minutes. When quicklime is used, it is generally spread dry. One method involves windrowing from pneumatic trucks, with the grader being used to form a lime blanket. With quicklime, the usual practice is to dry mix first, followed by heavy watering in order to start the slaking process, that is, convert the quicklime pebbles to hydrate. Additional mixing and watering complete the slaking in the soil, and ultimately a friable material results. On the Friant Kern Canal lining repair project in California, granular quicklime was used, with dump trucks handling the spreading. The lime flowed readily, enabling a uniform blanket to be laid down. Tailgate spreading, however, is not recommended for hydrate. On a quicklime project in Quebec, involving unusually wet terrain, the contractor modified a scraper for spreading by installing a hopper spreader in the scraper bowl. A vane-type feeder provided uniform spreading at a 3% application rate. Here, quicklime was specified for quick drying of the plastic clay so that it could be handled readily in the building of 25-foot-high sound barriers. The heat generated during slaking facilitated the drying action, especially in cold weather. That is not dust rising, it's steam formed during slaking. After mixing, the lime-treated clay was placed in lifts on the embankment and compacted. The strength imparted by lime enabled the sound barriers to be built on steep 1.5 to 1 slopes. Slurry made from quicklime is now available for stabilization, as shown on this pressure injection building foundation project in Dallas. The slurry is produced in a portable batch slaker set up on the job site. Water is introduced first, then quicklime is blown in from the tank truck. After slaking is completed, the slurry, at elevated temperature, is pumped at about 75 psi pressure into the injector rig. Each injection lance has a perforated tip for distributing the slurry in all directions. The lances are lowered hydraulically, with injections being made at 1-foot intervals, usually to a depth of 7 feet. Holes are spaced on a grid pattern on 5-foot centers. After injection is completed, the lime serves to reduce soil movement by forming stabilized moisture barriers. This novel lime injection system is also used on distressed railroad beds, often with fly ash added, in order to beef up support for the track and reduce maintenance. For especially deep-seated roadbed problems, this rig can inject slurry to 40-foot depths, using 3 independently operated lances. To the dry and slurry methods can be added central mixing of lime and aggregate, such as used on this I-90 project in South Dakota. The base course gravel was submarginal, and only 1.5% lime was needed to reduce the plasticity to meet specifications. Lime was fed by the screw conveyor on the right to the gravel belt conveyor, with water added in the pug mill mounted at the head pulley of the belt. The lime-treated clay gravel was then placed on the subgrade with an aggregate spreader and compacted. Here is one of several commercial crushed stone plants in California that produces lime-treated aggregate from clay-bearing crusher-run stone. Only 1% lime is needed to reduce the PI and increase the stability to pass state specs for Class 1 base material. The lime is screw conveyed from the silo on the left to the stone belt conveyor, and the materials blended before shipping. Central mixing is also employed in the production of lime fly ash base materials. The fly ash enters the collecting belt conveyor from the right, hydrated lime from the left, and gravel from the screen above. The three materials are then conveyed to a large twin pug mill, where water is added up to optimum and a uniform mixture is produced at a fast rate. Through the use of pozzolans like fly ash, lime stabilization can be extended from the plastic to the non-plastic aggregates. At Newark Airport, fly ash, lime, and cement were used to stabilize a sand subbase and a sand-crushed stone base mixture. 2 million square yards of pavement for runways, taxiways, and aprons were stabilized with thicknesses up to 30 inches. The strength gain imparted through the lime fly ash pozzolanic reaction was so substantial that total pavement thickness was reduced, effecting sizable savings. Yes, lime offers many advantages in construction, more than any other stabilizer. Foremost is the immediate reduction in plasticity and shrinkage. For example, on one project, lime cut the liquid limit of the Darnock clay from 70 to 41, the plasticity index from 35 to 9, and the lineal shrinkage from 21 to 5. Accompanying this change is an improvement in soil workability, as demonstrated at the Dallas-Fort Worth Airfield project. Depicted will be 4 construction steps in sequence: scarifying, disking, first rotary mixing, final mixing. Note in each step how the soil breaks down. What a contrast between the raw clay and the lime-treated soil. Lime also expedites construction by drying wet soils quickly, as illustrated on this highway warehouse project. Bags of lime were placed on the saturated subgrade and the lime dumped into piles. 30 minutes later, the water was blotted up about 3 inches to the pencil line. Note how the lime had been changed to a paste, indicating its great affinity to water. 4 hours after mixing started, the area had dried out drastically, a far cry from the earlier quagmire. An example of lime's waterproofing action is the Bergstrom sack base in Texas, where a 30-foot test strip of heavy clay was stabilized. 4 days after an 8-inch rain, the section stands out like a white ribbon. The ruts shown here were made by a D8 crawler tractor 2 days after the rain stopped. Tractor ruts are followed from the untreated subgrade onto the test strip, where they are barely evident. Continuing back to the untreated area, the ruts are 8 inches deep. Because lime is slow setting, it offers flexibility in construction. On this section, lime was mixed in, then the subgrade left for 2 weeks before being reworked without damage. Here, an unfinished lime stabilized base had to be reworked after it had raveled from weekend traffic during a torrential rain, again showing that reworking is possible after a short lapse of time. Now, let's consider lime's cementing reaction. This scanning electron photomicrograph of a lime-stabilized clay, enlarged several thousand times, shows the crystals resulting from the pozzolanic reaction between lime and clay. Further enlargement shows that the needle-like crystals interlock and bind the soil particles together, thereby imparting significant strength to the soil. How much strength? This clay, tested in the lab, reached 240 psi in 12 months, a 3-fold gain from the raw soil. Note that the strength increase was continuous, with most of the gain occurring during the first month. This clay gravel, stabilized with only 3% lime, reached 600 psi after 14 years, a 15-fold gain. Again, there was continuing strength gain, indicating the pozzolanic nature of the reaction. An attempt to salvage the stabilized gravel from this road during relocation was unsuccessful because it was so hard. Lime's cementing reaction is further demonstrated on this power plant foundation project in Illinois, where 20 feet of weak, silty clay soil was stabilized in lifts with 3% lime and 5% fly ash. This novel method of founding the building was specified rather than resort to more costly piles or concrete caissons. After stabilization, samples of soil were chipped from the wall of a tunnel dug into the foundation and placed in water along with the untreated soil. The latter fell apart quickly, while the stabilized soil resisted the water and remained firm. What a contrast! Now, let's switch to an actual job where the lime-stabilized soil performed underwater, the Friant Kern Irrigation Canal. The canal had exhibited many slide failures from expansive clay, so repairs were made by moving the clay to the canal bottom, adding 5% quicklime, mixing it in, then rebuilding the bottom and sides with the lime-treated soil, using the sheep's foot roller for compaction. How did the lining perform underwater? These sheep's foot imprints made during construction were still intact after the first irrigation season of 10 months' duration. The canal bottom was hard. It hadn't softened underwater. The engineer also had difficulty in penetrating the stabilized soil with a bar. In contrast, the adjacent unstabilized area was so soft that the bar could be pushed in easily. After 5 years of irrigation service, the sheep's foot imprints were still evident, and no further slides had developed. A true testimony to the permanence of lime stabilization, even underwater. Lime-stabilized roads also exhibit good durability. This street at Fort Hood, Texas, and this range road are still giving good service 25 years after construction. NLA's Bulletin 328 describes the pioneering stabilization work at Fort Hood and other military bases in the Southwest, which actually started in the late 40s. Generally, the only maintenance required, even for heavily traveled range roads, was surface treating every 5 years or so. In South Dakota, where nearly 1,000 miles of roads have been lime stabilized, the durability experience has also been very favorable. This graph compares 17 projects on the state secondary system surfaced with 1 to 2 inch mats. The lime-treated roads, on an average, incorporated 45% less gravel base than the untreated roads, yet experienced much less deflection, and only 1/4 of the maintenance cost, based on a 3-year period. A real savings. Lime-stabilized runways have also performed admirably. At Dallas-Fort Worth, pilots report that the runways, after 8 years of service and more than 3 million landings and takeoffs, are as good as when opened. That's quite a testimonial, considering that the airfield was built on one of the most expansive clays in the United States. The highway warehouse project, shown earlier, also represents a testimonial to lime stabilization taming an expansive soil. 23 years after completion, the warehouse building is still in excellent condition. In contrast, an adjacent building, which was not lime stabilized, cracked badly in only a few years. Whether lime is used in stabilizing building foundations or interstate highways, airfields or parking lots, railroad beds or canal linings, there are many benefits to be gained. Wet plastic soils are dried out, made watertight, and they are transformed into a firm working table for later construction. The stabilized layer also gains considerable strength, and the effects are permanent too. Pavements, whether rigid or flexible, remain smooth and durable for years to come. Based on these many advantages, engineers are regarding lime stabilization as a useful tool in all types of highway and heavy construction. In all cases, lime upgrades poor clayey materials into quality subbases or bases, and at low cost. Yes, with lime being applicable to all paving layers, and to a multiplicity of uses, to being used under the wettest of site conditions, and with various methods of spreading, wet or dry, it truly is a versatile soil stabilizer.